How's it going, class? This is going to be our seventh lecture of our course. I know this is saying chapter 8, but just keep in mind we're skipping around chapters a little bit, so don't look at this and be like, oh, I skipped chapter 7. If you're even paying that much attention, maybe you didn't even notice, but this is going to be chapter 8. Yes, this is the seventh lecture in the series, so you should be watching this one just after you watch the training for strength. Share my screen with you here, and we'll hop on into the lecture. All right, so training for speed and power. So you're going to notice that there's actually going to be a lot of overlap with this, with the training for strength. You're going to find that strength kind of comes in tandem with speed and power, not always, but usually the training styles that elicit adaptation for those three mechanisms are usually relatively similar to each other. You just kind of change the pace or maybe the intensity a little bit of what you're doing. So we're looking at power. Power is force times velocity. So force, we should know if you know your physics at all. Force is mass times acceleration, or FMA. And velocity is distance over time. And so for a short way to say this, is power is technically work done over time. So the more work you can get done, the more work that is produced by you in a shorter period of time, the more power you are said to be producing. So power and sports. There's a balance between force and velocity. So more muscle can generate more force. So you're saying hypertrophy and strength training can be good. So if you have larger muscles, you can usually generate more force. However, increased mass is harder to move. And just because you are developing the muscle's ability to maximally produce force does not necessarily mean that you are training it to develop that force quickly, right? Just because your car can go for a really, really long drive, let's say, on a tank of gas, does not mean that that car is a sports car and go really, really fast. It's the same concept here. As well as your anthropometrics, the shape of your body can alter how you produce power. This is why generally very strong individuals are shorter because you were more biomechanically advantaged for some sort of strength bout, as well as you will see for most, let's say, Olympic events like a race or cycling or athletes in the in track and field and in swimming. Almost all those athletes within a certain category, within a certain race category, are very similar in size. If you watch the 100-meter dash, most of the men in the 100-meter dash are somewhere between like 5'7" to 5'11". Some are a little bit shorter. That's why Usain Bolt looks so tall. I believe Usain Bolt is 6'3", but he looks like a giant in the 100-meter dash because he's one of the few individuals where his anthropometrics being out of the norm actually still benefits him. But for the most part, the most acutely beneficial anthropometrics for a 100-meter dash sprinter are all pretty much the same relative body size. So speed, as we should know, speed is a measure of a rate of motion in math terms. Speed is the distance traveled divided by time. Time it takes to travel that distance. So that's our speed. Speed is independent of velocity because velocity is just speed with a direction. And so speed is technically the magnitude at which you're moving, and velocity includes the magnitude in which you are moving and the direction in which you are moving. Now, power is a measure of the rate at which energy is transferred. In sports, power is force multiplied by distance divided by time. So work, which technically force times distance or displacement, is work over time. So it can refer to body weight, the weight of the barbell, or any resistance from an external source. So let's say like an opposing player. So the more power you have, essentially the more work and the more force you can produce in a shorter period of time. So we should recognize part of this, the force velocity relationship. So as you get more quick in your movements, as your movements of whatever you're doing increases, the amount of force that you can produce in that movement decreases. And we should all know this from lifting in the gym if we ever have. You find that lifting heavy loads is much, much more difficult because in order for the contractile units to develop that force, you need to move more slowly. And now this is combined with the power relationship. There is an optimal velocity and weight in which you can produce the most power. So obviously, if you have something that's very low force and very low velocity, that's not a lot of power, right? And now if we have something that's super, super quick, we're moving through the movement extremely fast, our power isn't very high because the amount of weight that we're moving likely isn't very high. And vice versa, if the force we're producing is extremely high, like a 1 RM, the velocity in which we can move that force or move that weight is not very high. There's kind of an optimal window where you combine force and velocity where you will get the most power output. So training for speed and power, very similar to muscular strength, the goal is to produce ATP at a higher rate for more force. So you're maintain and also to maintain that production longer. So if you can produce, if that crack of the firecracker that I've used before is louder, is bigger, if you can produce more ATP at once, that means more ability for the muscles to contract quickly. As well as for this, the aerobic system helps in recovery. So recovery using aerobic ATP production. And so if you are allowing for ATP pools to be replenished by not only anaerobic if you are allowing ATP pools to be replenished by anaerobic and aerobic pools, that is allowing for a greater starting point of your ATP pool, which will allow a greater force production or force output. So specificity determines anaerobic versus aerobic training needs. And so depending on what you are doing, if let's say you're a cyclist or you are a power lifter, the aerobic component is going to be different. A cyclist still wants really, really high muscular power and still really wants really, really high velocity, but they also want high amounts of endurance versus a power lifter doesn't care much about that endurance if they're only lifting the weight once. So they're more worried about that maximal rate of force development and that maximal ability to develop force quickly. So again, power duration relationship, this is much like the force duration relationship or like the intensity duration relationship that we see in aerobic sports, is that as power output increases here, right, we see that the duration of activity is much, much shorter. But as the duration of the activity increases, right, as the activity gets longer, our power output is going to decrease. So you can't maintain the same power output for a long period of time. You need to slow down that power output, and that comes from the mechanisms of fatigue that we talked about. So the power output you can sustain for theoretically infinite amount of time is called the critical power. And what that really would look like is, let me draw here. I'm going to erase the marks that I said. So this is on the right here. This is a general force velocity curve, or excuse me, a power duration curve. And so what you will see here is generally a force velocity curve will look very similar to this. Excuse me, I keep saying force velocity curve. I mean power duration curve. You will see a curve occur much like this, like you see here. And then this doesn't really show up, but you'll see kind of a plateau. You'll see a plateau. Ignore this little blip here, but you'll see a plateau of their power production. That essentially is what critical power is, because everything before that plateau, all this stuff over here has anaerobic contribution to it. And so if you burn through this anaerobic contribution, then you get to only aerobic contribution. And that essentially, remember, since it's the aerobic system, it can inevitably pretty much go on forever as long as you supply adequate substrate to it. And so if you do a 3-minute all-out test, which some of you, I don't think any of you were in my study last fall, but we did a 3-minute all-out test, and that is, or a critical power test, same thing. And that's exactly what it sounds like. You bike on a cycle ergometer, on a stationary bike, as vigorously as possible, as maximally as possible for 3 minutes. And what you will see is that power duration curve looks much like the one that I kind of drew here. You have that steep drop, and then you begin to even out, and you'll kind of get a flat line or a baseline in the last like minute to 30 seconds. And that is your critical power. That is essentially the amount of power that is being output specifically or directly by your aerobic systems. Here's a better, I suppose I should click more. Here's a better idea of what power duration curves look like. So if you are a very, very lactic individual, a person who is very, very adept in the anaerobic system and does a lot of power training, let's say an Olympic lifter, your power curve is going to be more steep. You're going to have a massive drop off more quickly. Versus if you have, let's say, you're a little bit more anaerobic lactic, you are a little bit more anaerobic and aerobically trained, you're going to have a little bit more of a drop off here, as well as this is kind of telling you the relative contributions of each energy system. So we have the phosphagen system here, we have the glycolytic system here, and we have the aerobic system here, right? Essentially, you're combining these things, as well as you can look at these in terms of athletes. These are your types of athletes that would be generally in these areas as well. And we see here the aerobic system, like we've seen many times before, takes a while to ramp up, and then it can continually produce ATP seemingly for a long period of time, if not forever. Also, power is position specific. So remember, we talked about the length tension relationship of muscles that you see down here. the length that muscle or the length that sarcomere is at is also going to dictate whether or not it can produce force. So we see here up at the very, very highest echelon of velocity, we have like a jump shrug, right? We have a jump shrug movement versus down here at the highest echelon of force and slowest or lowest echelon of velocity, we have a mid-thigh pull. And so each one of these different movements here, depending on what movement it is, might have a different optimal level of power. So I'll go back here. So we have this general power curve. This is just an average curve. Right? This is the average area where power is the highest for a movement. But what we're really seeing here is that each of these movements specifically has a velocity and force relationship in which you are able to produce the most power. So we're looking at this, we're looking at a force development profile, right? Which athlete has a better force profile? Well, this is a little bit of a trick question because it depends on what sport you're doing, right? So if you are, let's say, a sprinter, you're trying to move as quickly as possible. Well, you think about it here, if you're a sprinter, which one of these two profiles do you think will be better? Well, hopefully you said A, right? So because A, you were developing force much more quickly than if you were athlete B. So you get that greater jump in force more quickly. But athlete B might be better for, let's say, a strength bout. So when you are doing any sort of strength lift, like the world's strongest man, you have essentially unlimited amounts of time to move that weight, just as long as you can move it. And so even though you might have lower rate of force development, if you're athlete B, you have higher peak force development, and therefore it's more inducive or more important in your sport to make you a successful individual. And so force development profiles are very, very individual to what you want for a sport. Looking at this, are the classic strength lifts the best way to produce power? And what you're going to find is the answer is probably no. So when we look at this, we look at a traditional bench press, right? This is something that you would want to do if you are a well-trained individual. And as he does his bench press throw, you can also see here that his guide bars are set in an area that even if he were to drop the weights, he would not damage himself. He would not hurt himself. Obviously, this is something that you want to do when you are more well trained. But the idea here is that a traditional bench press throw is going to elicit more power adaptations because it's a more powerful movement. So we see the bench press right here, traditional bench press, right? And then we see the bench press throw. And really what this is if we remember for a bench press, remember you are only training the bottom portion of the movement. And so when you get to the bottom, that's the point that you were training. And then as you push up, the load feels lighter because you're more able to develop force. And because you're more able to develop force and the load feels lighter, you're actually not stressing the system as much when you're at, let's say, halfway down the movement versus fully extended. Um, Really, the only time you're stressing is the very, very bottom of the movement. But if you're doing a bench press throw, you are exploding through the entire movement. You are providing force and structure, or excuse me, force and stress through the entire movement so that you can throw the weights up into the air. And this is what's essentially known as the blow-by effect. When you have a weight, let's say on the bench or on the squat, and you only stress the bottom portion of that movement, you're really moving through the most important sport specific portion of the movement really, really fast. Because, like I said in my last lecture, when are you ever really at 90 degrees knee flexion in the sport? You're not. So, realistically, the most important portion of the squat to train is that top 15 to 20% that you actually use for jumping and pushing. But if you're using a weight that only trains the bottom portion of that squats, you're not really training the top 15% of that squat, and therefore, you're kind of blowing by it. But if you're doing a bench press throw or a squat jump, which I don't have here, but a squat jump, it has the same principle. You are exploding all the way through that concentric upwards phase of the motion, which is going to create more power adaptations than if you were just doing a traditional bench press or a traditional squat. So we're looking at here a core lifts absolute power that can be produced in our bench press or squat or deadlift. Right? These are the peak amounts of power. But if you look at our explosive Olympic lifts, our snatch, our clean, our snatch, our second pull, our second or our clean, our second pull of our clean, right? You see here that these movements elicit a lot more power. And that's why you see in any D1 sports gym, most of the lifting done should be Olympic lifts. Something you can do as well with this training is you can look at velocity-based training. So you're looking at the quality of reps versus only measuring quantities. So what you can do is you can bring an athlete in, so train an athlete where they're at that day rather than based on a percentage of the 1RM. So they come in, let's say before they begin the training protocol, and you see what their velocity is at each specific weight intensity. So at like 60%, 70%, 80%, 90%, and 100%, you see what the velocity is of that movement. Now, when you bring that back in for subsequent training events, you can also, again, measure the velocity of those movements. And you can see in real time, let's say you're on a Thursday, 3 days in your training cycle, and they're doing 60%, but they're doing it 10% slower than they normally do. You can either use that as an idea to encourage them more because maybe they're slacking off a bit, or maybe you're starting to overtrain them. And if you see that this begins to manifest over time, the velocity of their movements is getting slower, even though you're trying to train them to become quicker, you can use it to modulate your training and then make it more adaptive, make it more in tune with your goals of manifesting greater power gains. As well as, like I said, you can use it to motivate the athlete and measure fatigue. And so there's a few different ways you can do this. Most of the ways involve just tying a string to some sort of real apparatus, or you can tie like a GPS locator to the clip on the bar. And essentially you're just measuring the speed at which they're moving that weight. You type in, okay, we know that they have 70% of their 1RM in the bar right now. They're moving it at 0.7 kilometers per second, or whatever it would be, or 0.7 meters per second, not kilometers, fast, 0.7 meters per second. And we say, okay, that's slower than it's been the last couple of days. Either they're slacking or they're tired. What can we do? And we should back the weight off. There's a lot of different things you can do to modulate your training based on velocity-based training. So you can alter training based on position, sport, specific demands. So maybe your sport requires you to produce force more slowly. Maybe it's the opposite of what I was saying. Maybe you want to train for maximal strength and you're finding that their same relative strength now at 80%, they're moving more quickly than they used to, but they're not developing any more force. So their peak force is staying the same, but they're moving through each individual relative force or each individual relative weight more quickly. And you might think, okay, that means we're training a little bit more power than we want to be. We want to go back to training strength. Okay. Or more importantly, what it's mostly used for is what we're talking about here is muscle power training. You see that their maximal strength is going up, but their relative speed at each relative rate or each relative intensity is not going up. And so you think, hey, okay, we need to modulate the training to increase speed along with strength rather than just increasing strength. So adaptations to speed and power training. So this is going to be very, very similar strength training. So you produce ATP at a higher rate. You sustain that production for a longer time. You generate more force in the process. You recruit more motor units and increase myofibril content of the muscles. All these things should be really similar to strength training and things that we have talked about before. Similar adaptations, resistance training, like I said, not as significant increases in hypertrophy and strength. So power training, you're not going to see the same increases as you would see in hypertrophy in terms of size, or the same increases in myofibular content as you would in strength training. It's going to be kind of in the middle. So you get the fiber type shift towards type 2X. So that's more of your type 2A shifting more towards type 2X because you're increasing their ability to contract and produce force quickly. Increasing ATP, PCR, muscle glycogen stores, increase anaerobic enzymes, increase coordination and neural adaptation, increase buffering capacity. So these all make sense. If you're increasing your ATP and PCR and glycogen stores, you have more readily available energy for you, so you can provide a faster supply of energy to the muscle so it can produce force faster. As well as if you have increased coordination and neural adaptation, that means you're not wasting as much force, you're not wasting as much movement, so you can more acutely and more defined, in a more defined manner, move that weight in the way that you want to move it. If you're increasing your buffering capacity, remember buffering is for acidosis. If you are increasing your ability to fight off acidosis, which is fatigue, increasing your ability to fight off fatigue, that means that you are better able to perform for a longer period of time. And then finally, increase resistance to central fatigue. That might have to do with motivation. That might have to do with your self-perceived exertion. Something that you will find probably if you train novice individuals is that they train to the burn and not through the burn, as you might have heard before. People don't understand that that is a normal part of exercise. And therefore, when they start to feel it, they think that this uncomfortability is something that they should not be going through. But as you train, you begin to learn and understand inwards on yourself or intrinsically that you can actually push through that burn and keep on training. And so in neural adaptations for power training, we talked about this a little bit in strength training, but you have increased motor drive. So you have a better signal sent from the central nervous system. Increased firing rate, which we talked about, more and more impulses from the alpha motor neuron means more and more calcium release from the sarcoplasmic reticulum, which means more and more cross-bridge cycling from the muscle itself, which allows for a greater level of tetanus. And then increased motor unit excitability. What that means is that the motor unit is actually more able to be easily excited. So if you increase the motor unit excitability, that means it actually takes less of a stimulus to excite that motor unit. So you don't need to have as much motor unit drive, or excuse me, central nervous drive. And then decrease neural inhibition. So kind of like the Golgi tendon organ, you will find that as you begin more training, the inhibitory mechanisms in your body that are saying, hey, maybe we're working too hard, they begin to become less intrusive and they begin to diminish, which allows you to have a higher force output. So what we're seeing here is that an elite or stronger individual is going to produce power more acutely or more in a more extreme fashion than a novice individual. Next, we're going to talk about this stretch shortening cycle. And so this is something, if you've ever done a jump squat or if you've ever done a squat, right? If you wanted to see this in real time, you could do this right now. You could stand up in your room, hold yourself in a squat position at 90 degrees, hold yourself completely steady, and then without moving down at all, jump up. Now, do it again. Instead of this time, do a normal counter movement jump. Do the stand and then the down and then the up as high as you can. And if you have played any sports, you can imagine that the counter movement jump, the down and up, is going to provide you with a higher jump. And there's a few different reasons for that. But the stretch shortening cycle is something that we are going to talk about now. And so how that functions is with muscle spindles. And so what muscle spindles are is they are similar to Golgi tendon organs, but they are a little bit different. So Golgi tendon organs, when they sense extreme tension, they stimulate the muscle to relax so that you do not tear the muscle. The muscle spindles stimulate quick lengthening of the muscle. Excuse me, they're stimulated by quick lengthening of the muscle. And so quick lengthening of the muscle that's too fast can be damaging to the muscle. And so what the muscle spindle does is it senses that really, really quick lengthening and stimulates the muscle to contract. And that's what we see here in the patellar reflex. What you are doing is you are hitting the patellar tendon, which is causing a really quick stretch of the rectus femoris. And because the rectus femoris gets stretched really, really quickly, the muscle spindles stimulate that muscle to contract really quickly. And that is, in essence, is what the patellar tendon reflex is. And so these are somewhat opposite again of the Golgi tendon in that they sense muscle stretch and then cause the muscle to contract, versus the Golgi tendon organs sense muscle tension or the amount of force on the muscle and then cause the muscle to relax. So with this, it has to do with plyometric training. So it utilizes the stretch shortening cycle. So this helps bridge the gap between speed and strength training. So yes, you're really, really fast, or yes, you're really, really strong. How can we bridge that gap? How can we make somebody who's really, really strong, really, really powerful, really, really powerful? I have a list moment here. Really, really powerful, or how can we make somebody who is really, really fast, really, really powerful? And this has to do with the stretch shortening cycles. This allows you to transfer force quickly. What you're essentially trying to do is from your ground contact time in the eccentric to your concentric phase, you want to increase the amount of tension in your calf and in your tendons, which allows you to decrease the amount of ground contact time. And if you're on the ground for a shorter period of time, that means that you are essentially running faster. So the benefits of it: muscle damage leading to growth, loading of tendons and connective tissues, so they get stronger. So with this plyometric training, you are essentially loading the tensile portions of the muscle, the tendons and the titin, which you talked about before, and you are causing adaptations in those, which will allow for a greater transfer of force. This also may lead to bone mineral density and neuromuscular efficiency. And so I talked about you're improving the tactile or the tensile ability of the tendon. Essentially, you are increasing joint stiffness or muscle tendon stiffness. And so when you're trying to do rapid change of direction, tendon stiffness is actually very, very important. Obviously, you don't want to be quote unquote stiff or unflexible, but you want that tendon to maintain a rigid structure. You can think about it, if you're trying to pull a rubber band, you're trying to, let's say you tie a rubber band to something on the table, okay, and you have a very, very stretchy rubber band, you're gonna have to stretch that rubber band a long ways before you begin to move what's on the table. But if you take like a really, really strong rubber band or like a rope, which has like no tensile ability, and pull it, you're going to pull that object right away. It's the same idea here. If your tendons are too stretchy, the transfer of force from your muscles to your joint or to the ground is going to be lost in the stretchiness of that tendon. But if it's more stiff with that power training over time, the force transfer is going to be more complete and you're going to be able to change direction or move more quickly. So high load resistance training, plyometric training, and eccentric resistance training are the best way to increase muscle tendon stiffness. And that makes sense. You have a lot of force on it, you have a lot of eccentric load. So you're causing that tendon to stretch a lot. And what does it want to do when it's stretching a lot? Well, it wants to build structures so that it doesn't feel that same stressor, it doesn't go through that same stressor in as high of a capacity the next time. Another thing we're going to talk about here is called post-activation potentiation, or PAP. So you might have heard of PAP training. So essentially, this is short-term improvement in performance after completing a conditioning exercise at maximal or near maximal intensities. And essentially, the idea behind this is really just a very simple one that we don't fully understand yet, but you're in essence just kind of warming up the muscles. So it lasts about 20 to 30 seconds, up to several minutes. So the proposed mechanism is that there might be increased calcium sensitivity. So they think that if you do, let's say, a jump, which we'll talk about here in a second, and then you do some sort of maximal or near maximal lifting, you essentially are making the muscle cell more sensitive to the calcium release from the ceruloplasmic reticulum. And so therefore, when it does another contraction in a few seconds or in a few minutes, it is more able to quickly develop that force. As well as you are increasing the temperature of the muscle, there might be some ideas that the optimal level for temperature or the optimal temperature for muscle contraction is a little bit higher than where it is at resting, as well as you are increasing neural drive and muscle activation. So this has to do with that muscle excitability, as well as you were just essentially preparing the nervous system, in a way, and the motor cortex in a way that it's already activated and ready to send a signal rather than kind of jumping the signal on it. So the ideas and the theories behind post-activation potentiation are still in their mechanistic stages. We're still trying to see what's occurring and have a good explanation for what's occurring. There's not a lot of literature out there yet that really specifically says, hey, it's because of this, or hey, it's because of this. There's some speculation and there's some preliminary research that's saying, hey, it might be these things, but we don't know for sure yet. And what we're seeing here, though, is this is showing us what's going on. If we look at jump A here versus jump B, jump A, they just did a counter movement jump, and then they waited 8 minutes, and then they did another counter movement jump. And as we see here, the pre was actually a little bit higher than the post. So they actually dropped off a little bit, although I'm sure this was not significantly different, or actually it was not significantly different. Essentially what we're saying is if you do a counter movement jump, wait 8 minutes, then do another counter movement jump, they're relatively the same. But if you do a counter movement jump, wait 4 minutes, and then do a 5 RM squat, a near maximal squat, and then wait 4 minutes, the same rest time combined, 4 plus 4 should be 8, we should know. If you do the same rest time combined, and then do another kind of movement jump, we see here that your kind of movement jump is significantly higher. And so that is the manifestation of that PAP training. Essentially, with that post-activation potentiation, you have in some way geared the muscle up or geared the central nervous system up in order to provide it an opportunity to have higher rate of force development into your next movement. And we see here pre their torque and then post their torque, they actually develop force more quickly, more Newton meters, that develop more torque in their movement and allow them to jump higher. So we're looking at the correlation between vertical peak jump and sprint times. Essentially, most of sprinting is ground reaction force, or is vertical ground reaction force. And so you think about it, okay, yes, you're pushing off on the ground, to go this way, so it must be horizontal force. Well, it's actually mostly vertical force. Most of the force that you develop when you were running is straight into the ground. Because if you think about it, if the force that you were developing to the side, let's say you want to run this way, okay, my foot is hitting the ground, it's providing force straight down, and I also want to provide force this way so that I can move that way, right? I can move my foot that way. So if I put my foot into the ground, I have vertical force down. If you're watching me up on top here, I apologize, this isn't the best, but if you push down into the ground, if your horizontal force is more than your vertical force, you're going to slip. And you think about that, think about force vectors. If you have a force that's pushing you to the side more than a force pushing you down, you're going to slip. That's what sliding something is. That's how you slide something on the ground. All you have to do is provide a force that is stronger than the force that is holding it down, and you will slide it. And so what you're seeing here is that vertical jump is actually highly correlated with sprint times. Now you're looking at this and you're going, okay, you look at this and you're going, okay, well, 0.46 isn't very high. And what this means, what you're seeing here with these negative correlations, That's because sprint times, the lower your sprint time is, the faster you are, right? And so if we were to say sprinting speed, these would be positive R's. But essentially, this 7-meter sprint is an extremely strong relationship. This is very, very strong. This is almost unheard of in all of sports. As well as just a 40-meter sprint, we see that there's a still, again, over 0.4 is still a strong relationship. This is a stronger relationship than you will see in most athletic events. So that vertical jump carries over a lot into sprinting. We also have upper body power, so you can do chest throws, rotational throws, underhand throws. I'm sure we've all seen things like this where you throw med balls, you rotate, you swing a heavy bat, whatever it might be. Power is not intrinsic just to the legs, intrinsic to the entire body. Next, we're going to talk a little bit about speed and agility. And sprinting, for our speed and agility, sprinting has two phases. We have the acceleration phase, which we see up here, which is usually done in the first 40 meters of a sprint. And then you have 30 to 40, and then you have the top speed phase, which typically achieved 30 to 50 meters. And this is a little bit more technique based. So the acceleration is a little bit more have to do with your rate of force development. And then the 30 to 50 mark is a little bit more for technique based. And so we should know, as you get to top speed at about 6 to 7 seconds, you begin to peter out, you begin to slow down. And why? Well, because the phosphagen system is not providing ATP as quickly, and therefore you cannot have as high force output, and therefore you cannot run as fast. We see here at about 60 meters, we have our highest speed. Actually, a little bit more at like 45 to 50 meters here. But in this range here, we see max velocity, and then you're just trying to maintain speed, okay? And that's very, very technique-based. That also has to do with your phosphagen system being able to provide that ATP for a longer duration throughout that bout. The speed, stride length times stride rate. This makes sense. How long your stride is versus how many strides you can take. And so what the idea here is with Usain Bolt takes about the same amount of strides. We see him start to pull away here. We see this, he takes about the same amount of strides. If you're watching him with the individuals next to him, the stride amount is the same, but his stride length is longer because he is taller. And usually, like I said before, 100-meter dash sprinters are very, very similar in size because there's a proper balance between stride length and stride rate to provide for the highest amount of speed. But for some reason, Usain Bolt is physiologically and anatomically built a little bit different. And specifically for his physiology, he can somehow provide the same stride rates, even though his stride length is longer. In essence, that is why Usain Bolt wins all his races. He can turn his legs just as fast as everyone else. Because he's a little bit taller, somehow he's able to run a little bit faster. And so both of these are affected by ground contact time, hip flexor strength and power, hip extensor driving power, hamstring knee flexion, arm swing. Like a lot of power and a lot of form goes into being a world-class sprinter. So agility is essentially your ability to adapt or change. So agility can be viewed as an athlete's collective coordinative ability. So adaptive ability, modifying the action sequence upon observations or anticipation of novel changing conditions and stimulations. So your ability to adapt to any sort of change or any sort of stimulus as based on your observations. So you see something happen and you say, okay, I have to do this. You see your defender break down to the left, so you juke and you move to the right. You see your defender's hand move down towards the ball, so you move your hand, move your feet so that he can't reach it, whatever it might be. As well as balance. You need to have balance, static and dynamic equilibrium. You need to be able to change direction and change your motion without becoming unbalanced. Coordination, so combine multiple body movements into one action, as well as orientation. So you have to understand where you are. So not only do you have to combine multiple of your movements to make yourself change direction in the most efficient manner or move a bat or whatever it might be, in the most efficient manner, you also have to understand where you are spatially and have high proprioception in order to be able to properly change direction in the quickest possible manner. Reactiveness, so just well-directed responses and stimuli, and then rhythm, so observation and implementing a dynamic motion pattern, timing and variations. Essentially, all of these things together, you're essentially seeing a stimulus, you're adapting to it, and you're providing the most efficient change in what you are doing is what's going to equate to the highest level of agility. You see here, agility, we have a massive breakdown. I'm not going to go through this, but you can see how there's a lot of things that go into agility. Well, it's not just change of direction and speed, it also has to do with perception and decision making. So this is more of a breakdown of that. I'm not going to go through that. So summaries, this is a little bit shorter of a lecture I'm looking at. So remember, power equals force times velocity. Force is mass times acceleration. velocity is distance times time. I'm not a huge physics buff, but I do enjoy my physics. And if you're getting into any exercise field, you need to have a rudimentary understanding of this physics right here specifically. You're going to talk a lot about velocity, force, displacement, time, work, power. These are all things that you should know off the top of your head, and they're all things that you should be able to apply to your everyday prescription. There's a balance between size, force, and velocity. Obviously, if you were too big, you can't move as fast. So depending on the sport, depending on the demands of the sport, you're going to have a balance between strength and velocity. Maximum power output occurs at approximately 1/2 of the maximum shortening velocity. Based on our graph, you can see, go back and take a peek at that if you'd like. Plyometrics utilize the stretch shortening cycle, muscle spindles, and the active phase to increase muscle force development. So the active phase has to do with Titan. So we're talking about that here. The active phase of Titan. So you're trying to catch the Titan while it's still essentially wound around the sides here. We don't have to go too much into detail for that. It's a little beyond the scope of this class. But essentially, Titan is better activated if you were moving through a motion quickly. And so you were trying to utilize that using plyometrics. So speed is the acceleration and top speed phases. So you need to combine acceleration and top speed to have the greatest or have the smallest or lowest possible times in a speed-based event like 100-meter dash. The ability to change directions quickly and accurately is agility, which has a lot of different factors, specifically your decision making and your ability to develop force quickly. So always remember, select the best exercises based on the demands of the activity. You always have to have general preparation and general training, but once you get into sport and you want to be more specific for the training and make your athlete more elite, you need to make sure that you are supplying them the best exercises that meet the demands of their activity. The amount of time the athlete has and the resources available, you need to include as well for the specificity. You need to be training them in a way that's the most conducive to them, as well as you're getting the most bang for your buck. You're getting the most out of the training. This is going to be the end of the lecture there. This is the 7th lecture. I think we'll come back to chapter 7 a little bit later. Again, I'm going to say it. I'm going to keep beating this dead horse. If you have questions, reach out to me. I know this becomes a little bit more applied. This is more in the realm of athletic trainers, personal trainers, physical therapists, OTs. So if this is something that you want to learn more about, again, I'm by no means an expert, but I'm always here as a resource for you to reach out to. Even if you think your question is dumb, I'm going to try to provide to you the best information so that you can use this as a prescription tool as you go forward and help you out in the field. Otherwise, hope you guys have a good rest of your day.